Welcome to Oddly Real. I'm Nem Stefanovic. I'd like to talk to you about some unusual aspects of real numbers. Of course, I mean the numbers from the real number line. Numbers like 3, fractions like 1/2, and even numbers like pi. Most of us would assume we're quite familiar with these numbers and there's not much to talk about. But I wouldn't be too sure about that. Are you sure there aren't any gaps in that real number line? Did we account for all kinds of numbers that can be considered real? Would you be surprised if I told you that many real numbers don't have a unique decimal value? What if two sets, both containing infinite elements, were somehow different in size? We take real numbers for granted, but stick around and you might find them more interesting than you think. Now, if we look at the number line, we explicitly see the integer points, but it becomes immediately clear that there's much more than integers present in the real number set. There are a lot of points between the integers that fill the gaps. So what are those numbers? We can define a type of number on the real number line called a rational number. Rational numbers are a superset of integers, meaning that they include the integer values and a lot more. For example, 4 divided by 1 equals 4 is a rational number, but 4 is also an integer. But 1 out of 4 is also a rational number, but it is not in the integer set. There's a lot of these rational numbers to fill the gaps in between the integer values on the real number line. This would seem to fill in the gaps on the real number set, but unfortunately, it's not quite true. Since the times of antiquity, thousands of years ago, like in ancient Greece, people were already aware that numbers like the square root of 3 could not be constructed as a ratio of integers. In other words, this number is irrational. Another example is the number pi, which is also irrational. Yet both numbers belong on the real number line. Clearly, rational numbers are inadequate to fill the number line. There are gaps. This begs a bigger question. What other types of numbers might exist on the real number line that haven't been accounted for? Are there other gaps in the real number line? In order to find out, we use a systematic approach to represent every possible type of number that can be real. One way to do this is to define numbers as infinite decimal expansions. For example, we can take 1/4, which has the finite decimal expansion 0.25, but we can write it as 0.250000 and so on. Another example is 1/3, which is a rational number which already is characterized by an infinite expansion, 0.333 and so on. Then there are also numbers such as pi, which are irrational. This has an infinite expansion as well, but the sequence of digits is entirely unique. So pi equal to 3.14159265535 and so on. In other words, this approach lets us write any real number down with a decimal expansion out to infinity. Rational numbers are distinct from irrational numbers since they will have a decimal expansion that eventually starts to repeat. This is not the case for irrational numbers. The number pi is an interesting case, being irrational, since we can't fully write down this number using decimal notation. There is actually a single point on the number line that is unique to pi. Each extra digit that we include brings us closer to converging to that point. However, there's a very subtle issue that arises, not with irrational numbers, as unusual as they are, but with rational numbers. Remember, we said that we can write down an infinite decimal expansion for these numbers. But take, for example, the number 1. This has the decimal expansion of 1.000 and so on. But what if we tried to write the number down as 0.9999, etc.? Remember, this expansion is infinite. This is not the same thing as the number 0.999 or the number 0.99999. Those are finite values. Here, we can add arbitrarily more 9s, infinitely many, and the value approaches 1. It doesn't make any sense to talk about 0.999 etc., to infinity as a separate number. It's exactly equivalent to the number 1. But this situation isn't unique to the number 1. It happens for any number with a finite expansion. So for example, 0.15 can be written as 0.14999, etc. Strangely, the infinite decimal expansion of these numbers is not unique. They can be represented in both ways and represent the same number on the number line. We have two ways to write down the same number. Despite this strange situation of duplicate notations, it can be proven that this approach showing infinite decimal expansion does indeed show that the real number line is complete with no other gaps if we include both the rational and irrational numbers together. There's another interesting situation when we try to analyze the size of infinite number sets. But wait, why would I want to know the size of a set of infinite numbers? Isn't the answer infinity? There's actually more to it than that. To start, let's define one notion of the size of a set called its cardinality. That's the measure of the size of the set by counting its elements. For example, I have 5 unique cards in a deck of cards. We can say that it has a cardinality of 5. However, there are sets that also have an infinite number of elements. For example, the set of all natural numbers like 1, 2, 3, 4, etc. Strangely though, infinite sets can have different cardinalities. We will look at a simple example where we demonstrate two possible sizes of infinities, countable and uncountable. The uncountable infinite set is larger than the countable infinite set, meaning it has a larger cardinality. In order for two countable infinite sets to have the same cardinality or the same size, we need to arrange their elements in a list and demonstrate a one-to-one relationship between the elements of the two sets. For example, we can take the natural numbers, 1, 2, 3, 4, 5, etc., and compare them to the set of integers. Now, you might be tempted to say that the integer set is 2 times bigger than the natural number set. But remember, these are infinite sets. So saying 2 times infinity compared to infinity doesn't make sense. Instead, let's rearrange the integers side by side with the natural numbers. Notice that we can create a one-to-one mapping between the natural numbers and integers. Since every number in the integer set has a corresponding number in the natural number set, then we have shown that the two sets have the same cardinality, the same size. What about the rational numbers, numbers that can be any kind of fraction of integers? You can use those to create any kind of partial fraction value to any degree of decimal accuracy. Surely, there have to be many more of those than integers. Well, let's see. In this case, let's arrange the fractions as a 2D grid. Every point in the grid represents a fraction. For example, 0.11 is the fraction 0 divided by 1, and 0.12 is the fraction 1 divided by 1. We can traverse this grid in a linear path as shown, where we ensure to include every point. Strangely, the rational set of numbers is also countable and the same size as the integers and natural numbers. However, it turns out that the set of all real numbers is uncountable. Unlike the rational numbers, which are defined from integer values in a fractional form, you can prove that there is no way to create a list containing all of the real numbers. As such, there is no one-to-one mapping between natural numbers and the real numbers. The set of real numbers is larger than the infinite countable sets like integers and rational numbers. Countable sets are actually the smallest infinite sets. Technically, there are also different uncountable sets with different cardinalities, but we won't go into that here. I hope you found this episode interesting. Thanks again for watching, and remember, oddly real, really interesting.